If your computer makes a mistake right now, there's this ingrained, almost comforting expectation of what the consequence will be.
Right, you get a little spinning wheel of death.
Yeah.
Or an error message.
Exactly. The app crashes, you sigh, you hit force quit, you reboot, and your life just goes on because, the stakes are entirely digital.
You're contained.
Right. But what happens when that exact same software glitch, like that momentary processing error, happens inside a 500-kilogram robotic arm holding live artillery?
Yeah, the spinning wheel of death becomes very literal.
It really does. Today we're looking at the terrifying expanding gap between software that hallucinates and a physical world that just simply does not forgive.
Because we are sitting at the edge of this massive paradigm shift. I mean, for the last decade, we've been totally obsessed with building digital brains that can think faster, write code, generate art in the cloud.
All the fun stuff.
Right, all the fun, safe stuff. But now we're taking those incredibly powerful, but honestly incredibly flawed digital brains, and we're handing them the keys to heavy physical machinery.
And realizing we forgot to teach them how gravity works.
Exactly.
Welcome to the deep dive. Whether you're, actively tracking the future of industrial automation or you just casually use chatbots to write your emails, the mission today is going to fundamentally change how you view the machines around you.
It really will.
We're going to start at the extreme existential edge of heavy industrial robotics and trace that exact same danger all the way down to the keyboard where you're sitting right now. And to do this, we've got a really fascinating stack of sources.
We have an essay and a whole content ecosystem from an engineer who has actually lived in both of these worlds.
Right. Handling explosives and training language models.
Yes, which is quite the resume. And to ground all of this in our daily reality, we're also pulling from an internal Google guide on AI prompting. It reveals the exact psychological frameworks we have to use to keep these systems on track.
The connection between a heavy manufacturing floor and the search bar on your browser might seem distant, but the underlying vulnerability is totally identical. We are communicating with an alien intelligence that has zero native context for our actual world.
None at all.
Okay, let's unpack this, because there's a visual image in our source materials that serves as the perfect anchor for this whole conversation. Let me try to paint this picture for you.
It's a striking image.
It really is. It's this stark, brilliantly lit studio photograph. On one side of the frame, you've got a standard, sleek, black desktop computer tower. It's very unassuming, just a quiet little black box.
But right next to it?
Right next to it, completely dominating the frame, is a massive industrial robotic arm. It's made of this matte gray steel with these incredibly bold, heavy orange joints.
It looks like it could just crush a car engine without breaking a sweat.
Exactly. Looking at it, the analogy that comes to mind is that it's like looking at a highly advanced brain in a jar sitting right next to a heavyweight boxer.
Oh, that's a great way to put it. One is pure thought, and the other is pure physical consequence.
Right. The brain in the jar is entirely isolated from the elements. But the author of the essay uses this visual to define a concept called physical translation.
Yeah, and physical translation is basically the act of taking a digital command, like a line of code or a text output, and translating it into actual kinetic movement in the real world.
Turning data into torque.
Exactly, turning data into torque. And the author makes this really sobering argument that physical translation is the massive bottleneck the entire tech industry is about to hit at a dead sprint.
Which leads right to the central quote from the source material. This is the thesis statement for everything we're talking about today. The author writes, "Software forgives. Physics does not."
Software forgives. I mean, if you think about modern software architecture, it is built entirely around forgiveness.
The undo button.
The undo button. It's the most defining feature of our digital lives. If an AI generates bad code, a compiler catches it. If a language model hallucinates a bizarre recipe for cookies, the worst-case scenario is you eat terrible cookies.
Right. The feedback loop is harmless.
Exactly. But the moment you take that intelligence out of the black box and put it in charge of the heavyweight boxer,
When it controls the hydraulic pressure of that steel arm.
the undo button just disappears completely. And to understand why this is such an urgent crisis, we have to look at the author's background, because they aren't just a theorist.
Right. Early in their career, this author was a mechanical engineer designing robotic systems, specifically to handle live explosive shells.
Just imagine the daily reality of that. You're calibrating motors to pick up active artillery.
But then contrast that with what they do today. Now, they work deeply inside the generative AI space, training large language models on human empathy and conversational nuance.
They literally tweak algorithms to dictate how a chatbot responds to a stressed-out user.
When I read that, I was like, wait, what? Those sound like two completely different universes. From programming heavy machinery for bombs to engineering politeness in a digital assistant.
But the author points out a profound realization here. The ultimate goal in both of those environments is actually exactly the same.
Teaching machines how to safely interact with humans.
Yes. Whether it's kinetic energy and explosives, or a conversational agent dealing with human psychological vulnerability, the machine has to possess a fundamental architecture of safety.
Okay, I want to push back on this a little bit, though, because Silicon Valley became a powerhouse by living and breathing the motto, fail fast and break things.
Sure, rapid iteration.
Right. Push the update, see what crashes, patch it, push it again. That created the speed of innovation we have today. Why is that suddenly a bad thing for robotics? Why can't we just iterate our way to safe robots?
Well, the source addresses that exact tension. It comes down to the luxury of the beta test. Software developers live in a world of theoretical consequences.
So if social media breaks, they just roll back the update.
Exactly. The damage is virtual. But hardware engineers working in physical space do not have that luxury. You simply cannot beta test a bomb-handling robot on a live manufacturing floor.
Because failing fast with explosives is just a catastrophe.
Right. The author emphasizes that in physical engineering, safety is not a key performance indicator. It's not a metric you review at the end of the quarter.
It's a binary state.
Yes, a 1 or a 0. You are either perfectly safe or you are in critical danger. There's no acceptable margin of physical error when human bodies are in the same space as massive machines.
Which brings us directly to AI hallucinations. We hear this term all the time. It's when an AI confidently and articulately fabricates false information.
Right. It invents a historical figure or a fake event.
And to understand why that happens, you have to realize an LLM doesn't actually know things. It operates on complex probability math. It predicts the next most logical word based on billions of documents.
It's not lying maliciously. It just followed a math path that makes grammatical sense but has zero basis in reality.
All right, so keeping that in mind, let's look at the two scenarios the author contrasts. Scenario A is pure software. A legal chatbot hallucinates a fake precedent, a lawyer submits it, and it makes the news.
A massive PR crisis.
But what's the actual fallout?
It's contained, the stock takes a hit, an executive apologizes, they patch the software, and life goes on.
But scenario B is a 500-kilogram robotic arm on a busy manufacturing floor. What happens if that AI hallucinates a spatial coordinate?
What if it calculates the space to its left is empty, but a human is standing right there?
The author does not mince words here. The result is a fatal casualty. There's a line from the text that I highlighted 3 times. There is no patch for physical devastation.
You can't issue a press release to uncrush a human body.
No. You can't roll back the server to undo kinetic impact.
What's fascinating here is the fundamental disconnect we're facing. We are trying to take an intelligence built entirely out of language and math and force it to navigate the physical world.
The author says we're relying on neural networks that have never felt the sun.
Never felt the sun. They exist in server farms, they process text, but they have never interacted with the physical environment.
An LLM has absolutely zero concept of the physical weight of a payload. It can describe a heavy stone beautifully, sure.
But it doesn't understand inertia, it doesn't understand momentum.
And crucially, it doesn't understand human physical fragility. The sources use 2 contrasting environments for this, an automotive assembly line and a precision bioprinting lab.
Right, and those map the whole spectrum of physical forces. On the assembly line, you have macro-level forces, heavy steel, robotic welders, crushing pressure.
A miscalculation there is catastrophic.
Exactly. And on the other end, the bioprinting lab. The machines are microscopic, manipulating human cellular structures.
Tolerance is measured in micrometers.
Yeah. There, the danger is destroying incredibly delicate biological material with just a fraction of a gram of extra pressure.
But to the language model, those 2 environments are exactly the same, just different data variables. It completely lacks a native understanding of crushing force or microscopic delicacy.
So we've developed this incredibly smart software that is physically ignorant.
And the industry is racing to put it in heavy machinery. So what's the solution? The sources introduce a term for this: physics-informed AI.
Yes. Physics-informed AI. It's the realization that pure software innovation has hit a hard ceiling.
We can't just rely on algorithms that predict the next word anymore. We need systems that natively understand gravity, material stress, and inertia.
They need to understand physics as effortlessly as current models process a text prompt. If we connect this to the bigger picture, this is the core requirement for Industry 5.0.
Right, or embodied AI.
Exactly. Whether it's a warehouse robot or an autonomous truck, the tech industry has to make a massive shift. We have to move from building AI that simply talks to engineering AI that fundamentally protects.
From talking to protecting, that is huge, and the author is actively trying to start a dialogue about this. In our sources, there's a YouTube community post where they polled their audience.
It's a great diagnostic question for our collective anxiety.
Yeah. I want to pose it to you, the listener, right now. The author asks, when you look at AI in the physical world, what worries you most?
Are you worried about industrial robots making miscalculations? Or autonomous vehicles making edge case errors on the highway?
Or maybe the lack of government regulation? Or are you just totally unworried and trust the iteration process?
Well, if you look at the first two, industrial robots and autonomous vehicles, there's symptoms of the exact same disease.
Right.
It's that gap between confident software prediction and unforgiving physical reality. The failure mechanism is identical.
But while we wait for labs to invent true physics-informed AI, we still have to live in the present. We have to interface with these physically ignorant systems right now.
Which brings us to a fascinating pivot.
Yeah, we're stepping away from the hardware danger and zooming all the way into our everyday keyboard-level interactions. We're opening up the internal Google prompting guide.
Reading a manual on typing instructions into a browser feels like a massive leap from explosive shells.
It really does. But the conceptual bridge between these documents is wild. There's a highly specific line buried in the Google Guide that perfectly validates the robotics engineer's warnings.
It's incredible how these disconnected documents arrive at the exact same truth.
In the section called Always Evaluate the Output, Google explicitly warns that AI hallucinations happen most frequently, and this is a quote, when it's been asked to understand real-world knowledge and physical things.
Let's just sit with that. The multi-billion-dollar AI models reliably fail when asked to comprehend the physical world.
Google is openly acknowledging the blind spot. They explain it's because of the training sets. The AI was trained on text, not the sensation of mass or friction.
So because the AI has this native blind spot, who is responsible for keeping it grounded?
According to Google, it's us, the human operator at the keyboard.
We are the cognitive safety rail. We have to manually build reality for it every single time we interact, and our only tool for that is highly structured prompting.
Which opens the door to the anatomy of a perfect prompt. Google has this rigid four-part prompting framework.
It's basically how we put a leash on the brain in the jar.
Exactly. The four parts are persona, task, context, and format. Let's break this down with the example from the text. Say you want a tagline for a washing machine. Most people just type, "Give me a tagline for a washing machine."
Which is a recipe for a hallucination.
Right. Instead, step one is persona. The guide suggests you are a seasoned advertising writer. Why is it so critical to play make-believe with a machine?
It's not make-believe, it's math. An LLM is a chaotic ocean of almost every piece of digitized text. Shakespeare, Reddit, physics manuals.
It's all in there.
Right. So when you don't give a persona, you're asking that entire ocean to answer. But when you say you are an ad writer, you fence off 99% of that data. You restrict the probability space to marketing copy.
You're defining the borders of its reality. That makes so much sense. So step two is the task. Create a concise tagline. Simple action verb.
But asking for an action without surrounding reality is where the gears slip, which leads to step three, context.
I'll admit, this is the step I always skip. I just assume the AI will know what I mean.
And that gap between implicit human assumption and explicit machine requirement is where the danger is. If you just ask for a tagline, the AI has to guess what it's selling.
And when it guesses, it hallucinates. It might invent a nuclear-powered washing machine.
Exactly. So you must provide exhaustive context. The example says, the washing machine gets clothes extra clean, has 25 settings, and fits in a small space.
You're handing it the physical laws of your micro-universe. And finally, step four is format. Dictate exactly how the output should look, like use an active voice and be no more than 6 words.
Persona, task, context, format. You are engineering a highly restrictive corridor for the AI to walk down,
leaving no room for it to hallucinate. And to back this up, the guide has a secondary rule set.
Yeah?
The 3 C's. Be concise, be clear, be consistent.
The principle of being clear is huge. They specifically warn against vague language.
Oh man, they use the example of pasting a document and just typing, make this better. I do this all the time. Make this email to my boss sound better. And sometimes I get this bizarre Shakespearean declaration back.
Because better is totally subjective. Does it mean more professional? Funnier? Shorter? You're forcing the neural network to guess.
And guessing leads to hallucinations.
And the stakes stale with the physical reality. Vague prompt on a desktop. Weird email. Vague command to a robotic arm, like move the payload safer. Catastrophic misinterpretation.
The mathematical clarity is identical. Okay, so we follow the rules. Persona, task, context, format, 3 Cs. We hit enter. The AI spits out an answer. Are we done?
Absolutely not. The guide has a whole section on evaluating the output. We have to safeguard the software.
The 4 pillars of evaluation. We have to actively perform these checks. First is accuracy. Is it factually sound? Because the AI can't verify physical reality itself.
Right. The human must check it against the real world. The second pillar is bias. Does the output unfairly favor one demographic?
Because the internet is inherently flawed and biased, and the AI just reflects that.
Exactly. The third is relevancy. Did it actually perform the task, or did it veer off topic?
And the fourth is consistency. Did it stay in the persona the whole time, or did it start sounding like a Wikipedia article by paragraph 3?
These aren't suggestions. AI output must always be viewed as a starting point, never a final product.
So if it fails any of those pillars, we iterate.
Iteration is the true art form here. It's a continuous loop of feedback.
I love this analogy from the Google Guide. Prompting an AI is exactly like giving instructions to a brilliant, impossibly fast, but entirely literal-minded intern on their first day.
An intern with every book ever written, but zero real-world experience.
Right. If you give that intern a massive multi-layered project and say, figure it out by noon, they're going to panic and make huge assumptions. You have to break it down.
The rule is don't ask for everything at once.
The example they use is perfect. Step 1. First, explain the key principles of effective corporate decision-making. You just let the intern gather the concepts.
Then you evaluate that for accuracy and relevancy.
And if it's good, you move to step 2. Now, apply those principles to restructure my weekly status meetings. You lead it by the hand.
But what if it's still generating answers that are too theoretical? The guide suggests constraints.
Constraints are powerful mathematical boundaries, like adding, provide solutions that can be implemented within a single week.
That one sentence filters out any massive 6-month pie-in-the-sky ideas. It drags the intelligence down to the reality of your work week.
And if you need to be even more dictatorial, you use references. The guide uses an indie rock festival social media post.
Instead of saying be enthusiastic, you literally give it a reference text with the exact emojis and hashtags you want.
You give the literal-minded intern a precise template to mimic. Okay, there's one final deeply technical concept from the guide we have to cover because it perfectly ties back to our robotics engineer.
The context window.
Yes, the context window is the strict memory limit of the AI within a single chat session.
Imagine a physical desk. When you open a new chat, the desk is clear. But as you prompt the AI, you're laying documents on the desk.
Every follow-up question is more paper on the desk. And when the AI answers, it looks at everything currently on that desk.
Which leads to the non-negotiable rule of new chats. When you change topics, you must start a completely new chat.
If you don't clear the desk, cognitive disaster strikes. If you switch from finance to marketing in the same chat, the AI will combine them into a confused mess.
Now let's apply this directly to the robotics engineer's workflow from our sources.
This is where it all crashes together. The engineer drafted a deeply emotional LinkedIn post about their career. It talks about fatal casualties, explosive shells, extreme engineering tolerances.
So the AI's digital desk is overflowing with documents about extreme physical danger and life or death high stakes.
And then, immediately after, in the exact same chat session, the engineer asked the AI for an image thumbnail using the design philosophy of Dieter Rams.
Dieter Rams, famous for less but better. Hyper-minimalist, unobtrusive consumer design.
Right, so imagine the math happening here. You're asking for minimalist Dieter Rams design, but the context window is flooded with 500-kilogram robotic arms and explosive shells. What does this system do?
Extreme cross-contamination. It tries to blend unobtrusive design with artillery payload. You might get a hallucinated image of a beautifully minimalist explosive detonator.
It's catastrophically crossing the wires. You're combining the brain in the jar with the heavyweight boxer in a contaminated environment.
And while a weird image is just a glitch, that exact same cross-contamination inside the control software of a robotic arm is how you get a fatal failure.
Clearing the desk isn't just about better chatbots. It's a fundamental architectural safety protocol.
Absolutely.
The guide leaves us with one last, highly practical strategy: prompt libraries.
Don't reinvent the wheel.
Right. Once you've done the work, persona, task, context, format, iteration, save that prompt.
Build a personal library, but more importantly, share it with your team.
By sharing the exact sequence of words that keeps the AI from hallucinating, you are distributing a verified safety protocol. You're crowdsourcing the cognitive guardrails.
Until the day these systems inherently understand reality, we have to rely on those shared blueprints.
Wow. Okay, we've covered an immense landscape today. Let's trace this journey. We started with the realization that software innovation has hit a hard physical wall because physics does not forgive.
We looked at the extreme danger of fail fast and break things around explosive shells. A software glitch in the cloud is a PR headache. A hardware glitch is irreversible tragedy.
We define the need for physics-informed AI algorithms that natively understand gravity and human fragility.
Then we built a bridge to everyday reality with the Google Guide, showing that current AI hallucinates dangerously when asked to understand physical things.
And because of that native blind spot, the burden of safety is on us. We have to use strict prompting frameworks, evaluate for accuracy, iterate patiently, and manage our context windows.
This raises an important question, maybe the defining question of our era. Until AI natively understands gravity and fragility, what is our role? We are the safety mechanism. Our heavily iterated prompts are the only barrier between a useful tool and a dangerous hallucination.
We are holding the leash. And that leads me to a final, slightly provocative thought to leave you with today. Let's imagine the robotics engineer gets their wish. We actually build a true, perfectly realized, physics-informed AI.
Okay.
It perfectly understands human fragility. It understands pain. It comprehends the devastating physical consequences of a 1 millimeter miscalculation by a 500-kilogram machine. If we build an AI that deeply understands the terrifying stakes of reality to protect us, does that mean the AI of the future won't act like a fast, eager-to-please tech assistant?
Oh, well.
If we teach a machine the true stakes of fail fast and break things of the physical world, will that machine become incredibly cautious, agonizingly hesitant? Will an AI that finally understands physical consequence become so terrified of hurting us that it hesitates to act at all?
It's a profound paradox. The more natively safe we make the intelligence, the slower and more paralyzed it might become.
Something to keep in mind the next time you ask a machine to execute a task, whether it's writing a tagline or moving a piece of heavy steel. Thank you for joining us on this deep dive. Keep refining your frameworks, clear your context windows, and please watch your heads around those 500-kilogram robotic arms. We'll catch you next time.